Alright, welcome back. In programming, you have different ways of measuring the performance of an algorithm. For example, by measuring the seconds it might take your algorithm to accomplish a certain task. There is also another way of measuring the performance of an algorithm by taking into consideration the size of input and the number of operations your algorithm will perform to accomplish a certain task. In this video, we will introduce Big O notation, a new way of measuring the performance of an algorithm by taking into consideration the size of input and the number of operations your algorithm will perform to accomplish a certain task. We will take a look at of one constant time, of n linear time, of n squared quadratic time. We will also take closer look at different methods of array through the lens of Big O notation. We will also look at different methods of objects through the lens of Big O notation. By the end of this video, you will be able to look at your code and estimate how efficient it is. Let's get started. Well, think of Big O as a way to answer a simple question like this. So you can ask yourself a question like, if my input doubles, how much work does my algorithm do? So keep in mind that we are not measuring time in seconds because different computers have different speeds. Instead, we are counting the number of operations. So the fewer operations your algorithm performs as the input grows, so the better your algorithm is. Let's consider this function. So this function, all it does is to calculate the total sum of all elements which passed as an array through this function. So here we have a loop. This loop is going to run n times depending on the elements within an array. So coming down, you can see we are passing 5 numbers or 5 elements within the array as the argument to our function, meaning that the loop is going to run maybe 5 times. So, but the number of operations is going to increase as n increase or as the number of elements within array increase. For example, so we have this comparison operator. So this one will only happen only once at the beginning. So by this one will be happening every time. So we have this operator, comparison operator. We have this plus assignment operator, because this, when we have I plus plus, so it's like having I plus equal to 1. So meaning that we have two operations here. So we have this addition operator and this assignment operator. So we have this comparison operator, two operators here and two operators here. So what does this mean for the number of elements we have in the arrays? So as the loop is going to run 5 times, each operator here is going to happen n times or 5 times. In this case, we have 5 items. So this comparison operator, this is going to happen 5 times, these two 5 times, and this 5 times. This is going to happen 5 times, this assignment 5 times. So meaning that the number of operations will increase according to the number of elements we have in this array. So imagine if we have from 1 to 1 million items. So we will have 1 million operation to each operator. So we say O of 1 constant time complexity in big O notation when your algorithm performs the same amount of work regardless of the amount of data exists. For example, suppose let's say we have this array of 5 numbers. Let's say const numbers equal to this array. So in this case, getting any number within this array, it only required a constant time. Example, if we want to get this number 3, so we will say numbers, then square bracket, and then we have to pass the index where this number is. So we will pass the position of this number 3. So as you know, arrays are zero-based index, which means this one is at index 0, then this 2 at index 1, then this 3 at index 2. We pass the index 2. So in this case, we get the number 3. No matter the size of the array, so accessing element at index 0 or at anywhere in the array is the same. So it takes the constant time to get the element anywhere in the array. That's why we say it is a constant time. So we say it is a constant time because the time it takes to get an element at the beginning, in the middle, or at the end is the same. So when the time is constant, we simplify it to O of 1. So suppose if we have this array, suppose this array have elements from 1 to 100. So accessing element at the position number 2 or at index 2 and accessing element at index 99, which will give 100 if we have 100 items in the array. So this will take exactly the same amount of time. So that's why we simplify this to O of 1. Linear time complexity means the work grows proportionally with the size of input. So in other words, as the input grows, also the number of operations to perform grows. So let's have an example. Let's have an example, an array of numbers from 1 up to 10. 4, 5, 6, 7, 8, 9, then 10. So let's print these numbers by using a loop. So let's have a function which will accept this array and then print the numbers from 1 up to 10. Function, let's call it print numbers, and we will pass a parameter which will be the array, and then you have to print the numbers. So we will loop through this array and then we print each and every number to the screen. So we say for let I equal to 0, because arrays are zero-based indexes. Then we will go from 0 up to array.length. array.length, then I++. Then we say console.log array of I. So in this case, I have to call this function down below and then print. Then we will pass these numbers. So let's take this array down. Then we will pass this array in here. So the number of operations we have here will increase in proportional with the size of element we have in this array. For example, here we have 10 items, which means the number of work we have. So this loop will run 10 times. So imagine if we have maybe 5 million, from 1 to 5 million, then this loop is going to run 7 or 5 million. It will depend on the size of the items you have in this array. So the number of operations will grow proportional to the size of the array. So that's why we say it is O of n. This n means the number of, or the size, the number of input or the size. So in this case, we mean the items within this array. In big O's notation, we say O of n squared the quadratic term complexity. So when you have nested loops, for example, let's have a function which will print the pair of numbers. Say print pairs. So we have the first loop. Let j is equal to 0, then j is less than array dot length, then j plus plus. Then inside this loop, I want to have another inner loop which will start at the same position. Then I is less than array dot length, I plus plus. Then I want to display all pairs from this array. So I will print I array of, let's say array of I, and then array of j. Let's call this function print pairs. Let me pass 1, 2, and 3. So then let's run this function. I say example.js. So you can see now we have how many items? 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the pairs. We were able to print these pairs from the given array. So which tells us that every time we have nested loops, so we have For example, here we have 3 by 3 number of operations, 3 by 3, which is equal to 9 operations to perform. Which means if we have 100 items, now we are going to have 100 times 100 operations. So the worst case will be, for example, if we have like a million, like a million items, now it is going to be 1 million times 1 million operations. So in this case, you can simplify this to n times n operations, which is going to give us n squared. So it's going to give us n squared operations. So that's why we say it is of n squared time complexity. So this one. Now we are going to see the different array methods through the lens of big O notation. So we will begin by accessing the item of an array. So accessing item of an array, it takes a constant time. For example, let's say we want to grab this 20 here. So we say max, and then you have to pass the position of this 20. So the position is going to be 1. So this is because arrays are zero-based index, which means this 10 is at position 0, 20 position 1, then this 30 position 2, 40 position 3, then 50 position 4, then this 60 position 5. So by passing this index 1, then this will give us the number 20. So this takes the constant time because the computer knows where the location of, it knows where this index is located in the memory. So no matter the size of the array, accessing the number maybe at the beginning, in the middle, or at the end of the array, it always takes a constant time. So that's why we say the time complexity when we are accessing an item within an array, it is going to be of one time complexity. So it takes a constant time. Then let's move on to updating by index also. If you want to replace this 20 by another number, so all we need to do is to say max of 1. So we will put the index where this 20 is located. Then we can put another number saying 30. So in this case, so when we take a look at the entire array, let's say console.log max, and then let's see if this 20 has been replaced by this 30. Example 2. So you can see now I have 10, 30, meaning that this 20 has been replaced by this 30. So updating also an element within array, so it also takes a constant time. This also will be of 1. Then let's move on this push method. Push method. So this is done. This one too is done. Then we are on this push method. So push methods, we use it when we want to append a new value to the array at the end of the array. For example, if we want to add 17 here, so we say max dot push, and then whatever the value we want to append at the end of the array. So since we are pushing to the end of the array, so this is also going to take a constant time because the indexes are not going to change. So remember, this is at index 0, this one at index 1, this one at 2, this one at 3, 4, and 5. So when you are pushing a new item to the array, it is going to take a constant time by only adding 1 to the current or to the last index. It will be 6 if we are going to add a new number like 17. So this is not going to take much effort to our computer, so that's why it will take a constant time also to push or to add a new item to the end of the array. This also will take of 1 time complexity. So push is done. Let's look at pop. So the pop also, where the function of pop is to remove the last element from the array. So if we use pop method by saying max.pop, so this will remove this 17, this 70 from the array. So if we remove this, there is no extra work going to happen to our indices because we only removing this one, so the rest will remain the same, meaning there is no extra work to our computer. So also this will take constant time of 1 time complexity. So if you want to log this max.pop, it will remove the last item and return to the console. So you can see it is removing 17. It removes the last item. So this pop also is done. Now we are going to analyze shift method. So shift method, all it does is to remove the element but at the beginning of the array. So if we want to remove this 10, so we'll use shift method. For example, max dot shift. So it doesn't take any parameter. All you have to say is max or the name of the array, then shift. So here the time complexity is going to be O of n. So it will be O of n because if we remove this first element from the array, so there is something going to change to our indices here. For example, if this 10 is removed, so now you can see we no longer have 7 indices, which means this is 0 or one of these will be removed, and we have to rearrange our indexes. For example, this will come here and change to 0, and this will be 1, this will be 2, this will be 3, this will be 4, this 5, this will be 5, this 4, 3, just like this. 0, 1, 2, 3, 4, 5. You see. So you get the idea. What will happen is that there will be the rearrangement of the indexes if the first element is removed. So in this case, we say it is O of n because if we have a huge array, this is going to take a amount of time or the long time to rearrange these indexes, which is going to bring extra works to our computers. So that's why we say it is, we simplify to O of n. And then this same story goes to unshift. So when we use unshift, we are adding a new item but at the beginning of the array. So suppose if we want to bring back the 10 to the array, we can say max dot unshift and then put whatever the number I want to put at the end or at the beginning of the array. So if we put this 10 just like this, now we can see the number below the positions are going to mess up. So we need to rearrange again. So this will be 0, then 1 here, 2 here, 3, 4, 5, and then we need to we have another extra position here, which is going to be 6. So you can see indexes or the positions going to change. So this shift and shift, so you have to pay attention when you are adding or removing to the beginning of the array. So when you have a large amount of data, then think about it. So this also will happen to dot includes. Let's mark this as done. This one is done. And this dot include methods. So we use this include when you want to check whether a given value is included in the array, for example. So for example, let's say you want to see if 10 is included in this array. So we can say max dot includes 10, and then in this case, if we run this, you can see it is true, 10 is there. So this one. So this also, this includes method will take of n time complexity because it will need to visit each and every element in the array. So it will this take of n time complexity because it will have to visit the entire array, checking whether the given item is included within the array. So this is done. Index of also is going to be similar. This index of is going to have of anytime, because it will also have to revisit each and every element, checking whether the given element, checking each and every index and comparing to the number it will find to that index if it is equal to the given number. For example, if we are checking the index of 50, in this case, we say max dot index of, then it will, this index of method will revisit each and every index, and then it will compare the value it find at each position, then comparing to 50, and if it matches, it will bring back the index of this value. So due to the fact that it will visit each and every element, then this will take the several amount of times. Then in this case we say of n, because if the array is very huge, so it will take a lot of time to search for this value and bring back the index or the position. So the same goes to find method. So this find method, so this find method, we use it if we want to check whether a given condition is satisfied. For example, max.find, let's say we want to see if an item equals to 40, say const rate result equal to this. So it will bring back the item which is equal to 20, which is equal to 40, which will match this condition. Then let's log this. Also log result. So you can see it will bring this 40. So this will take off n, because this find method will also visit each and every element, comparing each item if it's equal to 40. So then it will bring the first item which will match the condition. So because this will visit each and every element in the array, so then this will result to of n time complexity. So imagine if you have a large number of array or a huge array, so in this case it will take a lot of time to search, because this will be a linear search, and then this is going to be of n time complexity. Then we move on to filter. This filter also work just like this find. So we will also bring the element which is matching the condition. Also this one will take of n time. Same to this map. This map, if we use a map, we use a map when we want to perform some operations, and then maybe in the end we want to bring back a new copy with a modified array. For example, if we want to bring the squared number of these arrays, each item squared. So we can have a new array. For example, let's say new array equal to max dot map, and we want to bring each item squared. Example, item squared. So if we log this to the screen, this array to the screen, now you can see each item here is squared. So this map also will have to visit each item individually and applying the functionality which is defined here. Then at the end we bring back a new copy of a new array with the functionality applied. So this also will take of n time complexity. So now here comes another one, reduce method. So we use this reduce method if we want to accumulate all of items from the array into one variable or into one value. For example, if we want the sum of all of these elements, so we can use the reduce method to do that. For example, you can say const result2 is equal to max dot reduce, and then this reduce will take two parameters. One is the accumulator, another one is current value, and then this will return the accumulator plus our accumulator plus the current value, and then we begin from 0. The accumulator will begin at 0, and then you can log this to the console and see what will happen. So now we are getting 290. So this will be the sum of all of these items. So remember, we are replacing 20 by 30. So if you are doing calculation, remember to consider these operations we did before. So this also will take of n time, because this reduce method will visit each item individually, then performing the defined operation, defined functionality within this body. So let's talk about this sum method. It's another method which we use when we want to check if any of this item satisfies a certain condition. For example, we can say if we want to check whether each and every number here is even number, so we can use sum. For example, we can say max dot sum, and then we want to see if item or the value do it like this. If value modulus 2 is equals if the remainder is 0. So in this case we will know that each value is even. So let's log this. This will return true or false. Let's log this to the console. Let's mute this one. So it is returning true because at least one of these, this 10 is even number. So that is why it is returning true. So in this case, it returns this true only because 10 is at the beginning, but imagine if this 10 is at maybe at million position. So in this case, it is going to take time to search for it. So this also it will require this some method to visit each and every element, so looking for a value or an item that can match this condition. That's why we say this sum method also has of n time complexity. Then this happen to every method. This every method also is going to it is going to behave like this one, but this will check if every item satisfies the condition. This every method of the array is going to take off n time because it will check whether each and every item from the array satisfies the defined condition. So every item has to satisfy the condition. So this will result to of n time complexity. So same goes to slice. This is slice method. So this we use slice method when we want to take some part of the array. For example, if we want to take maybe from 10 to 40, then I have to pass the indexes, the starting position and the ending position. For example, we can say max dot slice and then you want to slice from 0 because the first item is at position 0, and then if you want to end at 40, then if you want to bring the numbers including this 40, so this 40 is at position 0, 1, 2, 3 is at fourth position, and then you have to end at 5 position. This is because this slice will start at 0 position but not including the last position. So by adding 1, it will include the last item where you want to end your slice. For example, in this case, ending at 40. So in this case, this will take time depending on the size of the array. So that's why also this slice method takes of n time complexity. And then here comes another method, is concat, which also takes of n time complexity, because this concat we use it when we want to merge different arrays, when we want to merge two different arrays. For example, this will take of n. For example, we can concat, can say max dot concat, and then here we can pass another array. For example, 1, 2, 3, 4, and then 5. So let's log this down. So you can see now it is making a new array. So this will take off n time complexity. So it will take a lot of work to copy or to merge these two arrays. So that's why we say this concat method also will require of n time complexity. Then here comes another one, splice method. So we usually use splice method if we want to replace some elements or to add new elements or delete the elements. So this takes off n time complexity because by replacing or adding or deleting some elements, the arrays, the position of the elements within the array will need to be rearranged. So in that case, it will take off n time by rearranging the positions. That's why we say it is of n time complexity. Here comes another one, sort. This sort method, we use it when we want to sort items from the array. This is a bit different to of n time complexity. This will take of n log n. This will result to logarithm time complexity of n log n time complexity. So this is because sorting is much faster than the other methods. So we'll talk about this in future videos. And then this reverse method also takes off n time complexity. So this is because if you are reversing, maybe no matter the order you are reversing to, if you are reversing, so this is because if you are reversing, the order or the positions of the element is going to be to change. So that's why this is going to take off n time by rearranging the positions of elements from the array. So that's it for the array method through the lens of big O notation. Let's now take a look at object method through the lens of big O notation. So let's begin by assessing properties of an object. For example, so if we want to get the name, the username, can say user.name. So this will give us John. This will give us John. So this assessing the property, any property on the object will always take a constant time. So in this case, the big O notation is going to be O of 1. So no matter the size of an object. So this is similar to assessing elements in the array. So, and then the other one is inserting. So if you want to add another property, for example, let's say I want to add the city, you can say user.city, then you have to assign any city, for example, Kigali. So in this case, this also takes the constant time, which is going to be of 1. And then another one is the property which we use, the method which we use when we want to delete a property. So in this case, let's say you want to delete age, this age property, we say delete, and then user dot age. This also is going to take a constant time, hence of one constant time. Then we have other three methods. One is object.keys, object.keys. So this is going to bring a new array. Let's say keys here. Array of, this is going to bring the array of keys. Let's say keys or properties. Console.log keys. So you can see now we have keys. Since this age has been deleted, now we have name. We have name and the city. The age property has been deleted. So that's why you see name and city. So this will bring the array of all keys in the object. So this might take some time to create this array of properties. So it will depend on the size of the object. So assume you have a huge object. So in this case, this is going to take of n time. So it's going to take a linear time to create such array of keys. So hence of n linear time complexity. So then let's move on object.values. It is also going to take of n time. If we want to have array of values, let's say values is equal to object.values, and then you have to pass the name of the object. So in this case, let's log the values. So you can see this also create a new array with all values from the object. So now we will have the name and the city because the age has been deleted. So this also is going to take linear time, hence of n time complexity. Then last but not least is object.increase. This will bring an array of both keys and values in pairs. Let's say key value pairs. Let's say key values is equal to object.entries, and then you have to pass the name of the object. Let's log this key value pairs. So you can see now we have an array, but in this case you have an array containing a key and its value, a key and its value. So that's all. So this also will take of n time complexity. So that's all about object methods through the lens of big O notation.